Okay, so, hey, when's your first test?
Wednesday.
Your syllabus knows. You should put those dates on your calendar so you don't miss them.
Just like stay ready all the
They're
time.
Wednesday.
I think it's next week next Wednesday. Okay, so what I'm going to do, that means you won't have time to take an in-class quiz on chapter 5 and 6. What I will do is give you a take-home quiz on chapter 5 and 6 that's due on Friday. I'll give it to you Friday and it'll be due Monday. I can't grade it and give it back to you before your test, but I can post answer key to it, so you can check and see. And it won't be longer than a regular. It'll be like questions that could be on your test or something similar to it, so you just kind of see what I might ask you. That make sense? Okay. All right, so quick short lesson covering section 5.1 and 5.2. So we're going to talk a lot about how to not do statistics badly in this chapter, sort of stuff that you need to watch out for, biases you need to watch out for, things like that. And there are two major categories of statistical techniques that we're going to apply to data. The first one is the stuff we talked about a lot in the earlier chapters. This is called descriptive statistics. Descriptive statistics. And as its name suggests, you just kind of describe what's going on. You describe the relationship. You make no claims that, oh, this causes that or stuff like that. Some examples. What are some things that we made in the beginning? What were some graphical summaries that we drew? We drew histograms, yep. Histograms. We drew box plots, right? There was a pie chart at some point in time, right? So those are all graphical summaries. Some numerical summaries, as in numbers, we did, what's it called, like a 5-number summary, right? Things like that regression line. Yeah, that's the perfect size. That's a great calculator. Yes. Stuff like that. Does that make sense? So those are all examples of descriptive statistics. They describe your data. The thing we did in chapter 4, that hypothesis test, that's something called inferential statistics. I feel like I make my iPad spell check. Statistics. And that uses sample data to make conclusions about a broader range of individuals than just the people who were surveyed. Some examples include this chi-squared test thing that we did. And that was called, I did an example of something called hypothesis testing. Yeah, the null hypothesis is that there is no difference versus the alternative that there is is a difference. Okay. And what we're going to talk about a lot today is when can you use inferential statistics to say, okay, thing X causes thing Y? Over. So, inferential statistics can only be used when the data are a what kind of sample for the question being asked. The answer is a representative sample. Representative, which means you've got to think about the source of the data and the question of interest. So, for example, I shouldn't use the UAF women's basketball team to estimate the average height of women at UAF. That is not a representative sample. Does that make sense? Because there's a lot of them are probably tall, right? The same as I shouldn't use the UAF running team to estimate the average weight of women at UAF because, it helps to be thin when you run. But maybe this class could be a representative sample because, all the females in this class, because you are not, a certain body type isn't a helpful thing in statistics, whereas it might be in a sport. Does that make sense? So that's the idea of it being a representative sample. You kind of get all different people as opposed to one kind. So this is called the fundamental rule for using data for inference. And your available data set can only be used to make inferences about a much larger group if the data can be considered to be a representative with regard to the question and interest. Yes?
You missed a section in our paper.
I did?
Yeah.
I did. Of course. Thank you for telling me. So tell me whether you think the available sample data can be used to make an inference about a larger population. So could the heights of women in a psychology class, can they be used to estimate the average height of all women at a college?
Yes.
Yeah, probably. I would say so. So yes, women in a college class are probably a representative sample. Okay, how about this one? Parents of children attending a daycare facility are surveyed about whether the state government should increase funding for daycare providers, to provide lower rates for low-income families. The data are used to estimate statewide support for increased state funding of daycare. Yeah, heck no, something seems seriously wrong with that, right?
Yeah.
You would think no one would ever do this, right? It happens all the time. So, no, it's not a representative sample, as in parents may have different opinions than non-parents. Also, even parents just using daycare may have different parents than parents who don't have to use daycare because they can afford to stay home or they, stuff like that. What were you going to say?
Oh, these are parents of children. These aren't low-income parents of children.
Not necessarily, right? So
because right now there isn't funding or something. I don't know.
maybe there is funding, but they want to see if there's a to increase it. So it's.
Kids in the daycare so they can afford it. So they're not.
But maybe they still care. Maybe increasing funding might increase the level at which you get funding. Does that make sense? I think you might get daycare funding if you make below a certain amount of money. Maybe they would increase that threshold, which would affect some of these people. So I have no idea what question they're asking, but the point is they're really only asking parents when that isn't really telling you about statewide support, right? Because statewide support, those people are not parents or whose kids don't go to daycare. So all sorts of problems there. Okay. So populations, samples, and simple random samples. So the larger group of units about which inferences are to be made. So that your big, large group you care about, what's that called? Your population. So in your universe that you're looking at, that's everybody. And your universe might just be like UAF, might be your city, might be the whole world, your state, your country, something. A smaller group of units actually measured, that would be your sample. And if you take measurements on the whole group of interest, what's that called? It's called a census. And your census isn't hard if I'm censusing my whole class. You guys are easy to census. But censusing all of UAF, kind of challenging, right? Making you all take that survey that they've made people take, allegedly involved threatening to punish you with money, fines, things, right? We won't talk about that. Okay. So a political scientist surveys 400 voters that are selected randomly from the list of all registered voters in a community. The purpose is to estimate the proportion of registered voters who will vote. So what is the population of interest? Who do we care about? Do we care about all voters or just registered voters? I think in this case it is just registered voters. Do you understand the difference as opposed to all eligible voters?
Oh, eligible.
That's the word that's kind of thrown around a lot in an election year. People who aren't registered yet, right? But this one did say proportion of registered voters who will vote. People already in the system, so to speak.
Non-registered voters are people under 17 but about to turn 18?
Nope, a non-registered voter could be somebody who is over the age of 18 and just has never voted before, right? Or somebody who just turned 18 after the previous election cycle. It can be for lots of reasons, not just that, no. If you're too young, you're not an eligible voter because you actually can't vote. What's the sample? The 400 voters selected. Okay, in something called a simple random sample, every conceivable group of units of the required size from the population has the same chance to be in the selected sample. So this might mean that everybody that you have in your group has the same chance of being picked to be in your sample, and that's kind of like just saying I'll put you all in a hat. I'm going to randomly draw your names. That's the idea of a simple random sample. Put your names in a hat, not you in a hat. I'm not actually like magical. Oh man. And what are some advantages of a survey over a census?
Probably a smaller group.
Yeah, it's a smaller group, so I think a census might not be possible because it's too expensive, right? It costs a lot of money to train all those people and pay all those people, or too complicated. Do you agree with that? Like having to count every single person, you're probably liable to actually miss somebody. Does that make sense? And also it can take forever. It takes years to plan a census. Much less time is needed to plan like a really, really well-designed survey. And a survey may be more accurate because it's easier to train a small group of people to do your survey than a whole bunch of people to do the census. Does that make sense? So with the introduction of error, the probability that it's going to happen will be larger with more people. Okay, so we'll talk about names for things when surveys go wrong. So the first thing is a kind of bias that occurs when the method for picking people or participants produces a sample that does not represent the population of interest. This is called a selection bias. So it's when how you select people creates a problem. So, for example, choosing the whole UAF basketball team as my sample. I'm probably not going to sample a lot of short people in that sample, right? Okay. Something called non-participation bias. This occurs when a representative sample is chosen, but some of the selected people do not participate. Can you imagine that this happens all the time? Who actually says yes to people call them and ask for phone survey stuff? So I did so a few times. I'm like, oh my gosh, they need a representative sample. I should actually answer, be a good citizen. And then they kept calling me and they would ask me questions for like half an hour. I'm like, I don't have time for you. Leave me alone. I hung up on them. So this is a huge problem with like phone surveys. Mail-in surveys, right? Nobody got time for that. Even they're going to pay me. So sometimes they do. Like I was part of the National College Graduate Survey, and they follow you for like 10 years, and so they did like give me gift cards, which I forgot to use. But I mean, if I would have used them, I would have gotten $20. And they hounded me with like multiple like repeating like do this survey again, do it again. It was annoying. So I finally did it. And this last bias, called response bias, this occurs when participants provide incorrect information. This can happen because of how questions are worded and or the way the interviewer behaves. And it could also probably just be like lack of remembering. If you ask me about my eating habits for the last 5 years, I'm probably not going to remember what I had for dinner 5 years ago. It's just not going to happen. But this is quite common when you ask like teenagers about behaviors that are bad, or
Yeah, I was wondering about
stuff like that.
Lying,
Yeah, that's kind of lying, or you can so stuff like that. Actively lying, misremembering, or like just sort of underreporting how much you do something. If I asked you guys to report how often do you skip class, it probably is the case that you would underestimate the classes you've missed. Probably. But I'm taking attendance, so you missed fewer classes. So, okay. So we're going to refer to the 3 types of bias given above. Which type of bias would be introduced into each of the following situations? So this one should be the one that says, a list of registered automobile owners is used to select a random sample for a survey about whether people think homeowners should pay a surtax to support public parks.
Selection bias.
That's going to have selection bias. And it's not a huge problem in Fairbanks because lots of people own cars, right? But think about big cities. Do you see how that could really be a big problem in big cities like New York City? My husband's from St. Petersburg, Russia. Like, he still can't drive. So, he still hasn't passed his test. But, so, the point is, in big cities, lots of people own cars, and you would be picking a subset that was different than the whole population. So selection bias, only automobile owners are asked. This could be a big problem in cities. Or a problem. So, another thing that isn't clear is that if you have more than one automobile registered to your name, it would appear on that list twice or just once. Does that make sense as well? But that might also be a problem. Maybe your probability of being selected increases. And I don't know if that's true or not.
Could be they don't want a license.
They could, in which case, if you have more than one license plate to your name, you have twice the chance of being picked as somebody who only has one. So, okay. A survey is mailed to a random sample of residents of a city asking whether or not they think the current mayor is doing an acceptable job. Non-participation, right? As in, ain't nobody got time for that, right? A lot of people are going to throw that survey away, right? Or just not do it.
Are we supposed to just assume that they're going to not answer it? Because it doesn't really say they don't. So like.
No, but that's a common problem with mail-in surveys. Does that make sense?
I just mean like for this actual question, like if we were to answer something like that on a quiz. Because I mean, if I was going to make up stuff at the end of that sentence, I could say it'd be response bias too. Like they're all lying, saying you haven't made sure.
But why would they lie?
Yeah, I think there's no really good reason to lie about that one. Does that make sense? I think, and it is what you think, so I guess there isn't one that's necessarily super right, but with mail-in surveys, non-participation is really always a problem.
And also the people who hate the mayor.
That's a different kind. That's a different kind of bias. Yeah, that's something. It says a name. There's a name for that one. It's called. I have it in a second. I just kind of like have a brain fart. Okay. The university has decided to go to an online system of teaching evaluations, like as in here, like that happened last year, I think, right? And compared to in-class evaluations where I give you papers and say, fill these out now, what kind of bias do you think is present here? I think non-participation. Yeah, there definitely probably can be some response bias. Like somebody wrote on my evaluation last year that I was terrible at email communication. And that made me really mad. Because if anyone's emailed me, how long does it take me to respond to your emails? Less than a day, sometimes like less than 5 minutes. Yeah. So I just thought that made me kind of like mad. It's like, this is definitely not fair. I forgot your one email once and then it's like I'm terrible forever. I can't stay when you fill out surveys in class. I don't stay.
Oh, okay.
I mean, you've probably never done it this way, but back when we used to do surveys in class, the teacher gives them, and then they leave, and then you give them to some other person who have said, okay, you're going to bring them to the Wood Center wherever they went back when they did it that way. I'm not here. Well, that's not what it's like at college. So, no, I wasn't going to sit and stare at you. Okay, so those are examples. The bias that is introduced when you have strong opinions, that's called a self-selected sample. We're going to talk about that later in this chapter. I think it's the next section. So the last thing we're going to talk about today before doing your quiz is something called the margin of error, because this comes up in stuff that you're going to be seeing a lot in the news until November when this election is finally over. So you've heard a lot about polls and stuff that say, okay, this person has this percentage of popular vote with this margin of error, right? Have you ever heard? Maybe you have heard, maybe you haven't. It tells you that, okay, candidate X has 70% of the vote with a margin of error of 1%, which means it's that much plus or minus 1%. That's what they think the actual is. And one way to get that margin of error estimate is to use this formula 1 divided by square root of n, where n is the sample size, right? So, and this is something called a 95% confidence interval. It's a rough estimate of 1. And this is the amount, the sample proportion differs from the true population proportion, as in what the actual, say, proportion to vote for candidate X will be in most of the samples you take. Like if you repeatedly sample people, you're not going to get the exact same proportion every single time, right? That proportion is going to fluctuate a lot. This is the one that is kind of like most of the time right. And to make it a percentage, you do this. Just take the 1 over root n multiplied by 100%. Move the decimal over 2 spots, right? And an interesting thing is that this estimate is independent of population size. And there is a formula that depends on population size, but it's always going to give a smaller margin of error than this. This is overkill. Does that make sense? This is worse than the actual thing would be considering population size. And it's also really easy to compute, so it's used a lot for things like the current political polls that you see online, done by places like the Gallup organization. And to find the interval of, say, possible proportions, you take the proportion that you found from your sample, and you take away that 1 over root n times 100%. That's like the lowest it would be. And then add 1 over root n times 100%. That's the highest it's going to be. And this tells you that for about 95% of properly conducted sample surveys, that interval is going to contain the actual real proportion. Like, some of them won't, they'll be off, but 95% of them will. So we're just going to find that for a few things and talk about how to find the intervals. That's the hardest thing today, and it's not so bad. Okay, so some television rating agency produces the ratings of TV shows by asking a random sample of 5,000 households with TV sets what shows they watch. Find that conservative margin of error for this survey as a proportion and a percent. So just use the 1 over root n formula. So what goes in for n in this case? I think 5,000, right? Right, because the n is...
Oh, next one. Oh, yeah.
And if you punch that in a calculator, tell me what you get.
70.71.
No.
For root 1.
Oh, I'm sorry. Yes, do 1 divided by the root right away. Just do it in one go.
Okay. 0.014.
I got 0.014. Do you guys agree with that? Okay. And 3 decimal places will get you 1 decimal place after the percent sign. Does that make sense? So there's the proportion. What's the percent?
1.4%.
Exactly. So whatever they find, they're within they think they're within 1.4% of the actual value, plus or minus. In a random sample of 90 students at a university, 72 say that they use a laptop computer. So which one of those numbers is the sample size? 90. Okay. So 1 over root n is 1 over root 90. Let's give me both a proportion and a percent.
0.10.
I got 105.
Yeah, 105. So 0.11.
Let's do 1 decimal place after the percent sign. So 10.5%. Is that all right? Okay. And now we're going to find that approximate 95% confidence interval. So for that, we need 2 things. Thing 1, we need the proportion. In my stats class, we called that p hat. P P for proportion, the hat meaning it's the estimate, kind of like we had that Y hat thing before. Like you might sneeze. And you estimate that using your sample. What proportion of your sample had a computer? Laptop. 72 out of, which I think is exactly 0.8. Or 80%. Your interval is your proportion plus or minus this 1 over root n thingamajig. So on the lower end is 80% minus 10.5%. On the upper end, it's 80% plus 10.5%. Do you see what I mean by that? So what's the lower bound there? 69.5. And the upper is if you've taken more advanced classes, occasionally fuss about the kinds of parentheses on the ends of things. These are just parentheses, not brackets, so that's not as important here. Is that all right, how I got the interval? Okay. Sometimes the proportion is going to be already given to you. I tell you that it was 80%, and you've got to just do the plus or minus the margin of error. And the last thing we'll do before your quiz is talk about how should you pick your sample size. So what happens as your sample size increases, what's going to happen to this 1 over root n business? Is it going to go down or go up? Down. It's going to go down. Margin of error is going to decrease. And because of the rooting, how you make things more accurate you can't make something twice as accurate by doubling your sample size. What you have to do, so to cut your margin of error in half, you have to have a 4-fold, as in 4 times increase in sample size. So if your sample was 100, you want to make it twice as accurate, you have to go to 400 people. And I'm going to show you why that's true with some numbers. So if your n is 500, 1 over root 500, that's about 0.045 or 4.5%. And based on what I just said, what should the margin of error estimate for part B be approximately? About half that, so about 2.25%. And I think actually I got 0.0224. So that's 2.24%. Sample of 10,000, your error is actually exactly 0.01 or 1%. So can you see how that's kind of a large increase in people and not a very big gain in terms of margin of error? Does that make sense? Between 2,000 and 10,000, that's why lots of surveys probably don't have 10,000 people in them. So a lot of more people for not much gain, right?
Did you mean 2,000 into 1 over square root?
Yes. Yes, I did. And I'm going to go a teensy bit over, so I think we'll be fine, though. Your quiz is not that bad. The last thing we have, very, very last thing, is suppose you know the margin of error you want. I want you to find your sample size, okay? This is the one thing where you have to know a little bit of algebra in this class. Like this is one of those places, okay? So we want the margin of error to be 3%. So 1 over root n needs to equal 0.03. So how do you move the root n over to the other side? Multiply by it. Yep, so multiply by root n, and that gives you 1 equals 0.03 root n. And what do you do next to get that root n by itself? I wouldn't square yet. divide by 0.03, and that gives you 33.33 equals root n, and then you square, yep. So 33.33 squared is equal to n, and is about 1111.1. And I probably should have said, I shouldn't have said about, I should have said actually less than 3%, because this is one of those instances in math where you always must round up, if I worded that way. Using just 1,111 would give you an error that was a little bit bigger than 3%. So always round up, n equal to 1,112. And I don't want to go over any more. The last one is very similar and even easier because you